is our integrated model of climate change in London, which strings together and chains several aggregate models, each of which has been built by different groups of people. Now, that's another important issue, that certain aspects of certain key problems, etc., really can only be dealt with in a modelling and predictive context by stringing models together, the models themselves being the prerogative of different experts. So to some extent, this is as much to do with working with different experts as it is to working with different models in that sense. So integration in that sense. And the third example really is one bit of the second example where we're talking about visualization. Okay, so here is Metronamica, modelling urban development. Kirill has been modelling a slice of West London. He argues that this is a very typical slice of the development of the metropolitan area between 1870 and 2010. It's a very physically based model in that sense. A lot of what you might want to predict about West London is actually accepted as a given or a constraint within this model. So he's really predicting at a very fine spatial scale how land use changes. He's using this package Metronamica, which is a cellular automata model. Cellular automata model divides the world up into cells or parcels and basically makes the presumption that the change in any particular cell or location is a function of what goes on in its immediate neighbourhood and other constraints as well. So it's a relatively generic style of modelling in that sense, where they're arguing that the local context is all important in developing the emergence of the more global context in that sense. So here is his slice of West London, and what he's done is from old maps, really, largely ordnance survey maps. Then he's built, really, this is simply an example of how he developed it in that sense. He builds it at this parcel-based level, and these land uses are characterised from old land use maps and a whole variety of historical information in that sense. He builds a series of simple rules which are part of the Metronamica package. Here's the 1870 development to fix ideas. Heathrow Airport is on the bottom left somewhere, the bottom, and one of these is the Great West Road and the other the road to Oxford coming out, and this is sort of Paddington Station, sort of in the centre of London here. So this is a very small version of London with about 1 million people or so in 1870, perhaps 2 million at that point, but now, for example, Greater London is probably 13 or 14 million, and this is the situation in 2011. So what he's doing in this package is actually predicting how all of this fills in. Now, he accepts in this model that you can't predict something like Heathrow Airport. That's a kind of frozen accident. I mean, it was an airfield of some sort, and for a whole variety of idiosyncratic, accidental reasons, it became London's airport after the Second World War, etc. So there are several things, several big land uses in this picture that he's not able to produce. Here, for example, is the actual package itself. So that's what you see in the Metronamica framework, and you're seeing the 1870 and the final actual prediction in this particular context. And within this package, he's able to actually fashion a whole series of rules, to test a whole series of rules as to actually how this picture actually develops over time. And I should stress in this context that this, to some extent, is a descriptive model. It's difficult to predict with this model in some sense. It's easy to actually explain how local detail gets itself filled in, how the existence of a particular factory leads to an extension of the factory and things of that sort. So, to some extent, this is again an example of building detail, but building detail in such a way that the emphasis is on the detailed local rules, which then lead to the emergence of this particular structure. And currently, he's actually extending the model to other parts of London. Just go back to here. He's actually extending it to the whole of London in the sense, on the argument that this has worked rather well for West London. Because this is a very typical slice, if you go out of London anyway, then you see the same kind of historical type development, the Edwardian and Victorian era, through to the 1920s and then to the 1950s and so on. Okay, that's our first model, which is very different from the next set of challenges, and I think this slide showing a couple of points where there is detail that is difficult to predict in the set. Okay, now the need for integration. My second example, I'll go for another 5 or 6 minutes on these. My second example is the idea of integration, strict requirements for models. In this particular context, we need very long time horizons. We're looking at climate change in London. Climate change in London is largely related to sea level rise. If the North Sea was to rise 2 metres, then as indeed is an extreme forecast for the year 2100, then there are some really big issues about flooding in central London. There's been a floodplain problem for many years, etc. And essentially, to be able to say something sensible about what London's future development will be over the next 50 to 100 years, we need a whole series of models looking at employment, pollution, population and so on, and we also need to couple these with flooding models. And each of these involves different experts. One of the features is it's locked into a strong stakeholder process, that this particular project was to try and develop these integrated models in the context of a variety of stakeholders, the stakeholders being Environment Agency, Transport for London, GLA, Department of Communities and Local Government, etc. A whole series of what you call professional actors with a vested interest in policy. We're not talking about the public in general, but nevertheless the idea of putting these models into a context, making them visual, making them immediate, long-term predictions, etc. Many of the tensions involved in developing models are really contained in this particular project. Now, if you think we have a problem of flooding in a sense in London, these are the floodplains, etc. The top left represents the flooding in 1953, mainly in the Low Countries, but in Britain, for example, there was extensive flooding in the London area. You can see the little box there on the top left-hand slide, which is the Thames floodplain, etc. Great loss of life back in the 1950s, and the response, this was a tidal surge, etc. in the North Sea, extreme weather events, but essentially the response to that was put in place. It took 30 years to put the response in place. The response is the Thames Barrage, which is a big dam where they lower the gates for these surge tides, etc. You can see that this is the barrage in operation. It's a little bit east of the Millennium Dome, etc., east of Docklands. It has had a time life of, I think, something like 2060 or 2080. It's likely to be ineffective by 2040 because sea level rises, continuous sea level, or surge tides, I should say, which is implicated in sea level rise. In fact, that figure has probably come down to about 2020 now. So there's a major issue of actually doing something about the barrier, the Thames barrier, in the next 10, 15, 20 years. Because it took 30 years to put this thing in place by the time it's actually got built, in a sense. So what we're doing is building an integrated assessment of this kind of issue, this flooding issue. And we start with a geodemographic model that's built at the University of Leeds. It's a microsimulation model built by Mark Birkin and his people. And then that feeds into an input-output model built by Cambridge Econometrics, that's in the University of Cambridge. We build a land-use transport model, in a sense, which is highly visual. I'll give you a quick flavour of that in a moment. The whole of this consortium, the technical consortium, is handled by the University of Newcastle Geomatics Group, and they basically build a population site model. They also work on the transport networks, and they work on the flooding models. And the Institute for Transport at the University of Leeds are developing the emissions model, and another group in UCL and the Bartlett in the Energy Institute are working on the domestic energy. So all of these different groups are different sorts of people with different kinds of science requirements. All of these models were developed prior really to it, so it's a question of stitching them together. You can imagine the difficulties of doing this. That one of the features is that we're trying to make the interfaces as visual as possible, not simply to communicate these things to the stakeholders, you can see this stakeholder group above, but also to communicate them to ourselves. If I want to talk to flooding engineers, they don't really know much about trip distribution or location, etc. in this sense. They don't necessarily have a feel for the nature of the city. So to some extent, visualization is all important in this particular context. And here's an example of the of one stage, the GIS stage of the model, where you've got the GLA region, the London region in the bottom, and the black box represents the land use transport model, and then we're honing down to 50 metre per square before the flooding models come in. That's the population site model. Okay, now 2 minutes then on the sort of on the model itself, the visualization. This is an example of the desktop model. Let me just go back to the LUTM is the land use transport model, and this essentially is one version of it. It's built in a desktop version, so we can take it into the stakeholder meeting and we can actually run it on the fly, basically. We can actually develop scenarios in a visual sense, so this is the sort of splash screen with the data, etc. So we can actually develop a semi-professional kind of view of this. Most of our stakeholders are quite clever people. They're professionals in and of themselves. They're working with policy all the time. They can understand to some extent, as long as it's made intelligible, how these things are working. So that really shows you. This is a four-mode land use transport model. I'm just showing you the residential sector here. In London, for example, 38% of people travel by road. Most people travelling by public transport, other than that. So lots of visualizations. This is a picture of accessibility that comes out. One of the key features in this model is that at any stage we can actually use the same kind of visual analytics. So this is accessibility before we've calibrated the model. But once we've calibrated it, we can look at accessibility and we can look at it in terms of the future scenarios. And you can see the impact of congestion charging. If you think of red as being high accessibility, the blue bit in the middle of London is the congestion charging zone. Across that zone, it costs £8 a day. Here are some other visual analytics, tree graphs and things, etc. Now, if you actually want to see movies of this running, if you go to my website, and we have some movies there, so I've brought it up, okay, so go to the Science of Cities website, and there's a whole variety of movies. We've linked it to Google Earth, so if you click on this one, you'll see this desktop movie, this desktop thing in operation, linked to Google Earth. And this is our bigger model. This is the Arcadia model, which is the next stage, etc., which essentially is how we're actually making the model more detailed. Now, I'm almost on time in this particular context. I did hope to finish a little bit before, but we're not too bad in terms of that. And in fact, it's quite appropriate because my computer has got low battery, and I didn't plug it in, and it's actually hibernating. So at that point, I think I should stop. And if we have, I don't know, Nuno, whether it's appropriate to have questions, but I'm quite willing to answer one or two questions if you feel that's appropriate.